Hi there, I'm Seth Juarez, and I'm talking with Ron Gilad Bachrach and Kristin Lauter, researchers at Microsoft and Jung Cheon, a professor of Seoul at National University and a visiting scholar about privacy and AI. With big data and the cloud, privacy is really, really important. Thanks so much for being with us.
Thank you.
Thank you.
Okay, so why is privacy and AI such a big issue?
Well, so you can imagine as we go forward collecting more and more data from individuals and storing data from companies in the cloud, there could be major concerns about how this data is aggregated and used and shared with others that were maybe not the original intended recipients of this data. For example, let's say a person uploads their genomic data to some kind of storage site in the cloud, and they intended to use it to get some kind of personal prediction of their risk of having some kind of a disease. But if that data were stored there and then shared accidentally or intentionally with other parties, it could be used against them in some future situation. For example, there could be profiling based on genomic data that could lead to employment discrimination or lots of other kind of nefarious uses or scenarios you can imagine.
Interesting. So why is it a big problem?
You know, it's a big challenge because, you know, in AI, we're all about kind of infringing your privacy, right? We take all these small bits of information and come up with some interesting inferences about you. And now we want to say, no, we on one hand want to get the value that AI can give you, and at the same time preserve your privacy. And actually, you know, if you go back, AI, you know, we figure out ways. If I could get access to big data sets, then I can do all this magical thing that AI can give you. But in some cases, it's hard to get to these data sets. So they might distribute it, for example, between hospitals, if you want to do some medical diagnosis, or they might be distributed between different agencies if you don't want to do some national security kind of predictions. And without establishing mechanisms that can give you privacy and trust, you actually cannot get this data in order to run all these magical AI tools. So it's not just about, you know, preserving, it's not just the scenario that Kristin was talking about, it's also about our ability to run AI, right? So the fundamental idea of getting data might be impossible if you cannot build this trust.
So, I mean, it's a difficult problem. Because as data scientists, we just have this gold mine of data. We're like, oh, let's just work on it. Oh, and look, here's my interesting results. Let me just share the data with other researchers. But how do you protect people at the same time? I mean, that feels like a very difficult challenge. What say you?
Yeah, so this is why we bring together the expertise of these people coming from the field of cryptography and marry it with machine learning. So, you know, modern cryptography is more than just, you know, what we studied at school, kind of, okay, I encrypt the file and decrypt it when I want it.
Prime numbers is all I remember.
Yeah, exactly. So actually it's magic what they can do now, these guys. And they can actually have encryptions that allow you to operate on the data while it's being encrypted. So you don't have to decrypt it in order to do computation on this data. You can actually operate it on it while it's still encrypted. And this is magical.
But I mean, it feels like, because one of the things as data scientists is we have this data, and it's the correlations and the statistical distributions that are inherent with the data that cause the machine learning algorithms to work. I mean, I've always said machine learning is glorified counting. How do you encrypt data and still have those relationships exist in a way that they cannot be mined or reverse engineered?
Well, so one of the new techniques that we're using, which is very powerful, is called homomorphic encryption. This was a problem which was open for about 30 years in the community. And so it's very exciting that very recently, in the last 5 to 10 years, we started to come up with initially theoretical solutions and now practical solutions. Homomorphic encryption allows you to encrypt data so that you can still operate on the ciphertext, do computing, you know, just the basics that you need for machine learning, addition, multiplication, the circuits that you need to compute, and you could perform those directly on the ciphertext, and they still have meaning. They don't just turn into gobbledygook. The ciphertexts preserve their meaning as you operate on them. And the reason for that is that we're encoding them in an underlying mathematical structure. And the mathematical structure preserves the computation. So the homomorphic term is from mathematics, and it just means that computing can be done interchangeably with encrypting. So.
And that, I mean, and I'm because like I said, I remember encryption as prime numbers, right? Bob and Alice was in the textbook, you know. How do you preserve those relationships in a way that allows machine learning to work properly, but still not divulge information? I know I asked that already, but it feels like there's going to be some distributions that are in there that are going to be inherent in the data that are also going to be inherent in the actual ciphertext. How do we protect people?
So you can think of it, so imagine you want to compute things like averages or variance of data, just the basic kind of operations. So basically the computation itself involves just adding some numbers, multiplying them, and so on. You can do the same thing on the encrypted data, but the only difference being that you can't see the result because it's still encrypted. But you know that over here in the ciphertext, this is the average. I just can't read it. So I can really compute these values, but on your behalf, for example, I just can't see the result. The only way for me to see the result is send it back to you. You have the key and you can decrypt it. So I actually computed the average or the variance, or we're going to show here even more complicated functions. We can actually compute them. We just can't see the result.
So when so for example, let's just go into numbers, right?
Right.
When you're using this key, you're making everything all encrypted. You're saying that I can do math in the encrypted space, get an encrypted answer back that's right mathematically, but I don't know what it is in its original space. Am I getting this?
Exactly that.
That's exactly right.
Yeah.
Oh shoot! Well, we're done. Good job, everybody. So what is the? So you mentioned homomorphic encryption. What does that mean? Like, because I love terms, but I remember memorizing a lot of them in college and forgetting them.
So encryption just basically means you're taking information and you're encoding it in some way which makes it confidential. But the homomorphic term refers to the fact that you can interchange the order of encryption and computation. So homomorphic in mathematics just means that when you apply some map, you can either add and multiply things first and then apply the map, or you can apply the map and then do the computation. So that's what homomorphic means in mathematics as well, and that's what it means in this context here too. So homomorphic encryption at a high level, you can just think of it as encryption which allows you to still compute meaningfully on the ciphertext.
Interesting. And so because I remember when we had underflow problems, we'd go into log space and we had to change multiply to add and divide to subtract. Are there mathematical analogies to that in homomorphic space?
Yes, so in fact, what's really new and exciting about homomorphic encryption solutions that we've come up with is that they're based on kind of new mathematical primitives that had not been really widely deployed yet or used in cryptography. So they're based on lattice-based cryptography. Lattices are an underlying mathematical structure, and researchers have come up with clever ways to design encryption using lattice-based cryptography. And lattice-based cryptography is also not susceptible to known attacks by quantum computers. So it also fits into a big kind of revolution that we're experiencing right now, which is called post-quantum cryptography, which is the attempt to come up with crypto systems which will be resilient to attacks from quantum computers once quantum computers are built in the near future.
So for example, if we do these lattice-based encryptions that are homomorphic, we'll be able to protect this data now and for the foreseeable future, unless we come up with a new computational model.
Yes,
That's
exactly.
correct.
Wow.
So the thing to keep in mind, so in theory, homomorphic encryption allows you to take almost any computation that we do today and run it over encrypted data. But as you know, only in theory, there is no difference between theory and practice.
Of course.
So the challenge is performance. And this is kind of where we bring together our knowledge in machine learning and our knowledge in cryptography in order to make it efficient for the tasks that we care about.
I see. Because I've seen things encrypted that like I encrypt the number 1 and it blows up into some huge digit. are we having data size issues when we're going into encrypted space?
Yes, we have data size issues, we have computation time issues, all sorts of issues. And the challenge is how to make it. So many people think about homomorphic encryption as a nice theoretical construct, right? It keeps some mathematicians off the street, but is it something that we're going to see useful? And our goal is to make it something practical, to take problems that people care about and allow them to do them in a private and a very secure way. So this is what we're doing here, and this is why we bring together, cryptographers, mathematicians, machine learning, engineering, put all of them together and try to build something.
That's awesome. So now I feel like we've talked about it. I'm getting a sense for how it's working. Can you show me an example?
Yeah.
Absolutely.
Let me first show you an example of DNA prediction. So imagine you had your DNA sequence, and now it's pretty affordable, right? You can go out there and get your DNA sequence. And imagine there is someone that put a service on the cloud that can make some predictions on your behalf. Maybe you have a risk factor or something like that.
Sure.
But you might be a little reluctant of sending your just DNA over to this web service.
They might find out I'm Superman or something.
Exactly,
right?
exactly. So what we do here is allow you to send your DNA encrypted, right, to the service. And you don't send the key, it's just encrypted. So you send them this random bit string. They can run the prediction on your behalf, and you get the result. But they didn't see your data, and they even didn't see the prediction that they made on your behalf.
Clever.
So let's see that.
Let's go to the computer, yeah.
What we see here, this is actually a DNA of a flower, not the DNA of a human being.
Okay.
And what we want to predict is for a specific seed, how much time will it take it to generate a flower from the moment we seed it in the ground. So for this specific flower, the average number is 37 days.
Okay.
And I'm going to ask it to make the prediction. And again, this prediction is done on the encrypted data. So I sent the request, the server is now processing, and it took it about 2 seconds to generate the result that for this specific flower, it takes 29 days.
So for those that are at home, because you're not probably seeing the screen, they're getting it ready. There's a picture, like this reminds me of the old iris data set. Is that what this is?
No, it's actually a more sophisticated data set because it's really DNA. We have here 200,000 SNPs from the DNA. So we're really looking at the DNA, a large portion of the DNA. And we're encrypting it, sending a request to the server. It takes the server about a second or two to make the prediction. But the server doesn't see the DNA and doesn't even see the prediction that it makes.
And that's pretty impressive. And hopefully we'll get the demo up in a second so you can see what's going on. So effectively you have DNA of flowers that is all this encrypted machine. Because I'm thinking of like the model. Let's just say you're making a decision tree model. Right. The decision tree model is made over in the encrypted space. And so what you do is you take your data, you encrypt it, you give it to the model that only knows about encrypted data. Yeah. It produces an output. And that output, it doesn't even know what it is. Exactly. It gives it to you, you unlock it with your key, and then you get the data.
You can imagine that what you can do is you can take your DNA, encrypt it, and store it in the cloud. And you can be safe because it's encrypted. And every now and then when someone comes up with a new model, you can say, okay, here's my DNA, my encrypted DNA, run this, this prediction on my behalf, and I'll get to see the result, and nothing leaks.
And this is pretty impressive, and by the way, they're getting a demo because I want you to see it, because there are some legal implications, particularly in the European Union with data that's very, very, very specific. For example, I was at Croke Park in Dublin, Ireland, and they were taking pictures of crowds, and then they want to do machine learning over it, but according to EU laws, they can't upload that to the cloud. And so they had to do some stuff here, send some stuff there, and it feels like if they can encrypt all of their data and then move it up, they can do lots of work based on that.
Yeah, that's absolutely what we have in mind is that the cloud can provide simultaneously kind of storage of important data and also analysis. So it can enable a lot of new scenarios which are very relevant to AI. That's why we call it private AI, because it can be a way for us to access a lot of data and do learning on that data and doing predictions without compromising the data.
It feels like, though, I mean, let's just say we have tons of these machine learning algorithms out there. Do we all have to agree on the same kind of encryption? And then are all the models going to have to be relearned on this in this new encrypted space? Is there going to be a consensus? Do you see what I'm saying?
Yeah. So I think first of all there is a distinction to be made between the learning phase and the inference phase. What we demonstrate here is more on the inference phase when you already have the model, and we don't care how you generated it. You can generate it on the encrypted data, you can generate it on the unencrypted data. What we have to agree on is two things. Is one of the schema, how we represent the data, even on the clear. And then on the encryption scheme itself, and this is actually why we actually had just last week, we had a meeting with all the leading researchers and people from the industry working in this field, starting to work towards standards in this field to really allow these kind of applications to become reality.
And that's amazing, because now, for example, specifically, let's just say we're doing AI in the medical industry where the data is very sensitive and there's tons of laws that the government, we can now pass around data safely, build better models safely without having to sort of get other people's data everywhere.
Exactly.
All right, so it looks like we got our demo back. Let's take a look at what's going on here.
Oh, good.
So again, what we see here, we have here the flower,
Okay.
and we just click and ask the server to make to run the model for us. It takes it about 1 or 2 seconds, and it sends us back the encrypted result. We decrypt it, and we see the number.
Okay, so let me see if I'm understanding this right.
Sure.
There is a model in the cloud
Yep.
that has been trained on encrypted data.
In this case, the model has been trained somehow. We don't care whether it
We don't
was
know.
trained over encrypted data or not.
I see, and so, I see, which makes it even better,
Yeah.
because now we take this flower that's 29.1 that you're seeing there on your screen, and what we're doing is we're encrypting locally, sending this encrypted data up, and then when you push the button, it comes back and says, this is how long it took the server to do it. This is what the result is
Yeah.
for you.
Yeah.
But what the server's sending back to you is this gobbledygook.
Exactly.
So
That's
the
awesome.
computation was just the flowering time, and this particular flower, the flowering time was 29.1 days. That was the answer, and that's the answer that you decrypt once you get
And you
the
can-
computation back.
You can imagine if it was your DNA, maybe the prediction would have been something like, are you at risk of a certain disease or something like that? You don't want the server to know that.
I don't want any, yeah, because
Exactly. You want to know it,
Yeah.
but you don't want anyone else to have access to this information.
what are some other potential applications for private AI?
So we have another demo that you can see up on the screen now. This is a kind of simple example of image processing. So you can imagine image processing is a huge target for AI in terms of tasks and services we'd like to be able to provide. And in this case, what we're showing is handwritten digit recognition. So there's a well-known database
MNIST,
of
right?
MNIST of handwritten digits, and in fact, we've done this demo sometimes live where you can actually write the digit yourself.
Oh, that's cool.
And then what we do is we encrypt all of the images and send them up to the cloud so they're in encrypted form. And the neural net prediction happens on the encrypted data in the cloud. So the task here is just predicting what number is this. And it's a handwritten number. And so what you see in this demo is that we've actually batched together many different images and done a prediction. The prediction itself, in this case, took about 80 seconds, but it handled about 4,000 images in that time.
Wow.
So as we click through next, these are different images, different numbers, which have been predicted, and you can see in the yellow what our prediction is. The red is the initial image, and the prediction, the size of the number in yellow is our confidence in the
see,
prediction.
that's cool.
So most of these you'll see they'll have pretty high confidence, but there's a few where there's a little bit less confidence as to what is the correct prediction.
So you sent a batch of these up to the server, and it batch sent back. That's why is 80 seconds.
That's right.
That's pretty cool. I mean, and when I'm looking at this, obviously we're looking at the MNIST data, but you could imagine sensitive pictures. For example, I had a friend, and this is terrible, but he was a police officer that was trying to detect child pornography. Imagine the poor officers that have to go and sort through that. That'd be terrible. This kind of technology would make it so that they won't ever have to look at that. No one has to look at that kind of stuff, which is amazing. What's next for private AI?
So let me introduce one more example.
Okay.
It's a credit scores. So Korean government has very strong privacy laws. So banks has a challenge to generate credit scores, accurate credit scores from personal data. So we are working on designing a private machine learning algorithm which takes encrypted training set as input and output encrypted model. This model can be applied to encrypted private data to get credit scores. It's all done without ever seeing the private data.
I see.
Yeah.
And is this part of the demo is this another part of the demo?
Oh yeah, it's an interesting one. So homomorphic encryption has application beyond the machine learning. It can protect machine itself. That is, we can use homomorphic encryption to protect and authenticate control data in cyber physical system, such as drones, smart cars, and robots.
Oh, this is so now you're able. For example, you could send a drone bad information,
Yep.
but if it's not encrypted, doesn't have a key, it could never know what you're telling it to do.
Yeah, we can protect this one. So it can be used for protecting humans, like against dangerous AIs such as Skynet in Terminator.
All right.
Many people are worrying about this. Yeah.
I love this. There's certainly a privacy aspect to private AI, but then there's this safety aspect around private AI that allows you to actually control things from people who actually can and should control it. Well, we kind of ran out of time. This is really interesting. Thanks so much for bringing up both the problem and some potential solutions to the issues surrounding privacy in data-driven world. Your stories have brought sort of this topic to life. Thanks so much. Thank you, Kristin, Ron, Jung Hee, for that fascinating discussion about your work.